Hello everyone, hope you are all doing well. In this video, I will be solving the example problems of Class 12 Chemistry, Chapter 3 Chemical Kinetics. In this video, in detail, I'll explain that how a formula can be used to solve a particular problem considering all the example questions that's given in your NCERT textbook. Question number 3.1. From the concentrations of butyl chloride at different times given below, calculate the average rate of the reaction. So they have given the reaction of butyl chloride with water. We get butyl alcohol plus HCl during different intervals of time. Means we need to calculate average rate of the given reaction at different intervals of time. They have given us time in second, also concentration of butyl chloride. We have to calculate the average rate of the reaction and we have the formula R average is equal to minus change in concentration of the reactant divided by change in time. So this is nothing but in case of this equation, that's a reaction of butyl chloride. So change in concentration of butyl chloride, that is C4H9Cl divided by delta T, which is equal to minus concentration of butyl chloride at time T2 minus concentration of butyl chloride at time T1. So this gives us change in concentration divided by T2 minus T1. So using this formula, we shall calculate the average rate of the reaction. So from the given time as well as concentration of the butyl chloride, we shall tabulate them and we shall write concentration during time T1 and T2 and the corresponding time interval T1 and T2. Using that, we will calculate the average rate. Now let us tabulate these things. Tabulating the data that's given. So time T1 is the initial time, that is 0. So the corresponding concentration is 0.100. T2 is 50 seconds. So time T2 is in second. T1 is also in second. Concentration is given in terms of mole per liter, that's molar. Both the concentration in terms of molar. Okay. So time interval T2, corresponding concentration is 0.0905. So similarly, now the concentration 0.0905, we will consider the time interval. And this concentration changes to 0.0820. Now the time interval is 50 seconds and 100 seconds. Similarly, noting down others, now the concentration is 0.0820. Its next concentration is 0.0741. Time interval here is 100 seconds and 150 seconds. Similarly, next, now the time interval is 150 seconds and 200 seconds. So corresponding concentration 0.0741 and 0.0671. The next time interval is 200 seconds and 300 seconds. Corresponding concentration is 0.0671 and 0.0549. Next time interval 300 seconds and 400 seconds. Corresponding concentration is 0.0549, 0.0439. Next 0.0439, 0.0210. Corresponding time is 400 seconds to 700 seconds. And the last they have given time interval is 700, 800. Corresponding concentration is 0.0210 and 0.017. So we have tabulated the data. Now we shall use the formula for average rate, that is minus of concentration of butyl chloride at T2 minus concentration of butyl chloride at T1 divided by T2 minus T1. Now let us calculate the average rate constant at different time intervals one by one. So for the first case, average rate is equal to minus of 0.0905, which is the concentration of butyl chloride at T2, minus 0.1 divided by 50 minus 0. Okay, so this is equal to minus of 0.0905 minus 0.1, which is minus 9.5 into 10 to the power minus 3 divided by 50. So minus into minus plus divided by 50 is 1.9 into 10 to the power minus 4. So the answer here is 1.9 into 10 to the power minus 4. Now if we come to the unit of average rate, here in the numerator we have concentration terms, which is mole per liter, and in the denominator we have time in the unit of seconds. So the unit of average rate is mole per liter per second. Now coming to the second, here concentration at T2 is 0.082 minus 0.0905, which is equal to minus 8.5. Minus of minus, that would become plus 8.5 into 10 to the power minus 3 divided by 100 minus 50, which is equal to 50, which is equal to 1.7 into 10 to the power minus 4 mole per liter per second. So third, it is minus of 0.0741 minus 0.0820, which is 8 into 10 to the power minus 3 divided by time interval T2 minus T1 is 150 minus 100, which is 50. So 8 by 50 into 10 to the power minus 3 is 1.6 into 10 to the power minus 4. Fourth one, minus of 0.0671 minus 0.0741, which is equal to 7 into 10 to the power minus 3 divided by 200 minus 150 is 50, and that's equal to 1.4 into 10 to the power minus 4 mole per liter per second. Fifth, minus of 0.0549 minus 0.0671, which is equal to 0.0122. Now divided by time interval is 300 minus 200, that's 100, which is equal to 1.22 into 10 to the power minus 4. The unit is mole per liter per second. Next, minus of 0.0439 minus 0.0549, which is equal to 0.011 divided by 400 minus 300, that's 100, which is equal to 1.1 into 10 to the power minus 4. Next, it's minus of 0.0210 minus 0.0439, that's equal to 0.0229 divided by 100, that's equal to 2.29 into 10 to the power minus 4. Last, 0.017 minus 0.0210, which we have to multiply with a minus sign. So we get 4 into 10 to the power minus 3 divided by 100, and that's equal to 4 into 10 to the power minus 5 mole per liter per second. If you want to express 4 into 10 to the power minus in terms of 10 to the power 4, you can write this equal to 0.4 into 10 to the power minus 4 in the unit of mole liter per second. So this is how you can find the average rate for different time interval for the given reaction of butyl chloride. Question number 3.2. The decomposition of N2O5 in CCl4 at 318 Kelvin has been studied by monitoring the concentration of N2O5 in the solution. Initially, the concentration of N2O5 is 2.33 mole per liter, and after 184 minutes, it is reduced to 2.08 mole per liter. The reaction takes place according to the equation 2N2O5 gas giving 4NO2 gas plus O2 gas. Calculate the average rate of this reaction in terms of hours, minutes and seconds. What is the rate of production of NO2 during this reaction? So here we need to calculate average rate of reaction in terms of hours, minutes and seconds. Also we should calculate rate of production of nitrogen dioxide. So first let us calculate the average rate of reaction. So average rate of reaction is equal to minus change in concentration of N2O5 divided by delta T. But if you look into this equation that has been given, we see that stoichiometric coefficient of the reactant N2O5 is 2. Therefore, average rate expression should be divided by 2. So we have average rate is equal to minus 1 by 2 delta N2O5 concentration, change in concentration of N2O5 divided by delta T, which is equal to minus 1 by 2 change in concentration of N2O5. So the final concentration is 2.08 mole per liter. Initial concentration is 2.33 mole per liter divided by delta T. So they have told in 184 minutes this change in concentration is observed. So which is equal to minus 1 by 2, 2.08 minus 2.33, that's equal to minus 0.25 divided by 184. So the unit here will become mole per liter. Minute from the numerator will go to denominator, that will become minute inverse. Simplifying this, minus into minus plus 0.25 divided by 2, which is further divided by 184. So we get the answer 6.79 into 10 to the power minus 4 mole liter inverse minute inverse. So this is average rate of the given reaction in the unit of time, that's in minutes. Now we need to convert this answer into the unit of time in hours as well as in seconds. So converting minutes into hours, we'll do it first. We know that 1 hour is equal to 60 minutes. So now I need hour in the numerator part. So I'll write this as 60 minutes divided by 1 hour is equal to 1. So I'll multiply 6.79 into 10 to the power minus 4 mole per liter per minute into 60 minutes divided by 1 hour. So this is the unitary method that I am doing here. So minute inverse and minutes gets cancelled with one another. So now this average rate is equal to 6.79 into 10 to the power minus 4 into 60. The remaining units, let's write, it's mole per liter. This R from numerator will go to denominator, that is R minus. So this is equal to 6.79 into 60, which is equal to 4.076 into 10 to the power minus 6 mole per liter per hour. This is the unit in terms of hours. Now let us consider the unit, we need to convert it into seconds. 10 to the power minus 4 mole liter per minute. So here we will use that. We know 1 minute is equal to 60 seconds. So 1 minute divided by 60 seconds is equal to 1, and we will multiply it here. 1 minute divided by 60 seconds. Minute and minute inverse gets cancelled. Now we need to divide 6.79 into 10 to the power minus 4 by 60. Unit is mole per liter per second. So 6.79 divided by 60, that's equal to 0.113, which I can write as 1.13 into 10 to the power minus 5 mole per liter per second. So this is how we can convert the unit of average rate from minutes to hours and seconds. So we have represented average rate in terms of minutes, hours as well as seconds. We have calculated the average rate of the reaction. Also in the question they have asked us to calculate the rate of production of nitrogen dioxide. So rate of production of nitrogen dioxide is this is equal to delta concentration of nitrogen dioxide divided by delta T. Means change in concentration of nitrogen dioxide with respect to the change in time gives us rate of production of nitrogen dioxide. Now from the given equation, we can write rate of reaction in terms of rate of formation of nitrogen dioxide. So since we have the stoichiometric coefficient of nitrogen dioxide as 4, we have to divide it by 4. We have delta concentration of nitrogen dioxide divided by delta T. So in this equation, delta concentration of NO2 divided by delta T is nothing but rate of formation of nitrogen dioxide. So this is equal to 4 into rate. So we have calculated rate of the reaction, that is 6.79 into 10 to the power minus 4 mole per liter per minute. So multiplying it by 4, we will get the rate of formation of NO2. So 4 into 6.79, we get 27.16. So I can write this as 2.716 into 10 to the power minus 3 mole per liter per minute. So this is the rate of production of nitrogen dioxide. Question number 3.3. Calculate the overall order of a reaction which has the rate expression. First one, rate is equal to K, concentration of A raised to half, concentration of B raised to half. B, rate is equal to concentration of A raised to 3 by 2 into concentration of B raised to minus 1. So for any reaction like A plus B giving products, we can write rate law as rate is equal to K concentration of A raised to X into concentration of B raised to Y. So for this rate law, order of reaction is equal to X plus Y. So order is given by the sum of powers of the concentration in the experimental rate law. So for A, they have given us rate is equal to K into concentration of A raised to half, concentration of B raised to 3 by 2. So here we have X is equal to half, Y is equal to 3 by 2, and therefore order is equal to X plus Y, which is equal to half plus 3 by 2, which is equal to 4 by 2, and the order is equal to 2. Similarly for B, we have X is equal to 3 by 2, Y is equal to minus 1, and therefore order is equal to X plus Y, and that is equal to 3 by 2 plus of minus 1, which is 3 by 2 minus 1. So which is equal to 1 by 2 or 0.5. So order of reaction is half or 0.5. Question number 3.4. Identify the reaction order from each of the following rate constant. So they have given K is equal to 2.3 into 10 to the power minus 5 liter per mole per second. 2. K is equal to 3 into 10 to the power minus 4 per second. So here let us see how we are writing the unit for rate constant. So we know rate constant is nothing but it is rate divided by concentrations of the reactants. Right? This is written from the rate law that we have rate is equal to K into concentration of A raised to X and concentration of B raised to Y. We know that order of the reaction is X plus Y, and this order I'll write it as N, which is equal to X plus Y. So here I can write K is equal to rate is nothing but concentration divided by time, and the unit of concentrations we have in denominator, that is raised to N, because it is order of the reaction. So if I consider SI unit of concentration as molar, that is mole per liter, and for time the SI unit is second. So I can write unit of K is concentration, that's mole per liter, divided by time, it's second, divided by concentration to the power N, that is mole per liter to the power N. Further simplifying this, I can write this is mole per liter per second, then mole per liter to the power minus N, which is equal to mole. This will become mole to the power minus N, so I can write 1 minus N, liter to the power minus 1 plus N and second inverse. So this I can write mole to the power 1 minus N, liter power N minus 1 per second. So in general, I can write this as unit of K, that is mole raised to 1 minus N and liter raised to N minus 1, or if I consider this mole per liter as molar, so then I can write molar to the power 1 minus N, second to the power minus 1. Now, in order to find order of the reaction using the value of rate constant that they have given, we shall compare the unit of K with the unit of rate constant that is given in question number 1 and 2. Now first question, we have K is equal to 2.3 into 10 to the power minus 5 liter per mole per second. Now let us compare the unit of rate constant that's given. It is liter per mole per second. Okay. So now I'll compare the unit of liter that's given in the question as well as with the general expression. So from that I can write N minus 1 is equal to 1. Right? So N is equal to 1 plus 1, which is equal to 2. And therefore, rate constant that's given in question number 1 is corresponding to a second order reaction. Here N is order of the reaction. N is equal to 2 tells that it is second order reaction. Also you can check with moles. We have mole power 1 minus N is equal to mole power minus 1 in the question that's given us. So I can write 1 minus N is equal to minus 1, and therefore N is 1 plus 1, which is equal to 2. Either with mole term you can verify or with liter term you can verify. So considering the concentration term, we can identify rate of the reaction. Now moving to the second question, they have given K is equal to 3 into 10 to the power 4, 10 to the power minus 4 per second. So here clearly you can see that unit of rate constant is only in terms of time. So clearly it is a first order reaction, because we know that rate constant for a first order reaction is told in terms of only time. In terms of concentration, rate constant for a first order reaction is not possible. So it is second inverse, that's inverse of time. So the second question, its rate constant that's given is with respect to a first order reaction. Question number 3.5. The initial concentration of N2O5 in the following first order reaction, N2O5 gas giving 2NO2 gas plus half O gas, was 1.24 into 10 to the power minus 2 mole per liter at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 to the power minus 2 mole per liter. Calculate the rate constant of the reaction at 318 Kelvin. So, the reaction they have given is N2O5 is getting converted into nitrogen dioxide and oxygen. So, the initial concentration they have given us, so it's N2O5 concentration at time 1 is 1.24 into 10 to the power minus 2 mole per liter, and the concentration of N2O5 after 60 minutes was given. So N2O5 it is 0.2 into 10 to the power minus 2 mole per liter. So time T1 I can consider it as 0 minute, and T2 I'll consider it as 60 minute. So we are asked to calculate rate constant of the reaction. Okay, so we have the formula rate constant K is equal to 2.303 divided by T2 minus T1 into log of initial concentration divided by the final concentration. Substituting 2.303 divided by T2 minus T1, it is 60 minus 0 minute, log of concentration initially it's 1.24 into 10 to the power minus 2 divided by 0.20 into 10 to the power minus 2 mole per liter in both numerator and denominator. So gets cancelled with one another. 10 to the power minus 2 also gets cancelled. So it's 2.303 divided by 60 log of 1.24 divided by 0.20. The unit is minute inverse. Simplifying, 2.303 divided by 60, that is equal to 0.03838 log of 1.24 divided by 0.20, which is log of 6.2. Unit is in terms of meter. When you check log of 6.2 in the log table, you will find it as 0.7923. That has to be multiplied with 0.03838 into 0.03838, which is equal to 0.0304 minute inverse. So this is the rate constant of the reaction. Question number 3.6. The following data were obtained during the first order thermal decomposition of N2O5 at constant volume. So they have given the corresponding equation. 2 N2O5 gas giving 2 N2O4 gas plus O2 gas. So they have given us different time interval and the total pressure during the given time interval in atmosphere. Calculate the rate constant. So we need to calculate the rate constant corresponding to the reaction that they have given. The reaction is 2 N2O5 gas giving 2N2O4 plus O2. So now at time t, the pressure of reactant is 0.5 atmosphere. So this is the total pressure. Since no products were formed initially, their pressure will be 0. And the total pressure is nothing but it is the pressure of the reactant. Now at a time t, let me consider the pressure of the reactant N2O5 decreases by X. So since we have 2 moles of X, that's reactant that's reacting, so I write 0.5 atmosphere minus 2X will be the pressure, and X will be the pressure of the products that is formed. So pressure of oxygen at the time interval T will be X atmosphere, and it is X atmosphere for N2O4. Since 2 moles are there, it is 2X atmosphere. So at a time T, I can write total pressure PT is equal to 0.5 minus 2X plus 2X plus X. So minus 2X plus 2X gets cancelled with one another. So I can write total pressure is 0.5 plus X. And from this I can write X is equal to total pressure minus 0.5. The pressure of N2O5 at a time t is 0.5 minus 2x. Let us substitute for x, that is 0.5 minus 2 into pt minus 0.5. Simplifying this, 0.5 minus 2 pt minus into minus is plus 1. So this is equal to 1.5 minus 2 pt is the pressure of N2O5. Now at t is equal to 100 second, they have given that the total pressure is 0.512 atmosphere. This is given in the question. So from this we can write at t is equal to 100 second, pressure of N2O5 is equal to 1.5 minus 2 into total pressure, that's 0.512, which is equal to 1.5 minus 2 into 0.512, which is 1.024. This comes out to be 0.476 atmosphere. So from the given data, now we have calculated the pressure of nitrogen pentoxide initially as well as the pressure of nitrogen pentoxide during the reaction. So now using this pressure value, we can calculate rate constant by using the formula K is equal to 2.303 divided by T into log of P naught divided by PT, where P naught is the initial pressure of the reactant divided by PT is its pressure at time interval T. Now making use of this equation, let us calculate the rate constant for decomposition of N2O5. We have the initial pressure of reactant is 0.5 atmosphere, and at a time interval of 100 seconds we have calculated the pressure as 0.476 atmosphere. Time interval is 100 seconds. Now let us calculate rate constant, that is 2.303 divided by 100 seconds into log of 0.5 atmosphere divided by 0.476 atmosphere. So the unit of pressure get cancelled with one another. We are left with 2.303 divided by 100 into log of 0.5 divided by 0.476, that is equal to 1.0504, and the unit is second inverse. Find the log of 1.0504 using the log table and you will get log as 0.0213. which has to be multiplied with 2.303 and we have to divide it by 100. So into 2.303 divided by 100, that's equal to 4.9199 into 10 to the power minus 4 per second. So this is the rate constant for the decomposition of nitrogen pentoxide at the given pressure during the time interval of 100 seconds. Question number 3.7. A first order reaction is found to have a rate constant K is equal to 5.5 into 10 to the power minus 14 per second. Find the half-life of the reaction. So they have given us rate constant K for a first order reaction. It's 5.5 into 10 to the power minus 14 per second. We need to calculate half-life of the reaction. So we have the formula. For the half-life of a first order reaction, it is K is equal to 0.693 divided by T half, or T half is equal to 0.693 divided by K. That's equal to 0.693 divided by 5.5 into 10 to the power minus 14 per second. So we have to divide 0.693 by 5.5, that's equal to 0.126. So I can write this as 1.26 into 10 to the power 13 seconds. It is just a seconds. So 1.26 into 10 to the power 13 seconds is the half-life. Question number 3.8. Show that in a first order reaction, time required for the completion of 99.9% is 10 times of half-life, that's T half of the reaction. So for a first order reaction, we know that rate constant is equal to 1 by T natural log of initial concentration of the reactant to the concentration of reactant at that time interval. For 99.9% completion means I can write concentration at 99.9% completion. Remaining concentration is R naught minus 0.999 R naught. So this much amount of reactant will be left over. So rate constant is 1 by T ln of R naught divided by R naught minus 0.999 times that of the initial concentration. So this I can write as 2.303 divided by T log of R naught divided by, taking out R naught as a common term in the denominator, 1 minus 0.999. So R naught and R naught gets cancelled. So we have K is equal to 2.303 divided by T into log of 1 by 1 minus 0.099. It's 1 into 10 to the power minus 3. So which is equal to 2.303 divided by T into log of 10 to the power 3. This is equal to 2.303 divided by T into 10 to the power 3's log is 3. So we have K is equal to 2.303 into 3 divided by T, that is 6.909 divided by T. So this is the rate constant for a first order reaction for its 99.9% completion. Now the rate constant corresponding to half-life for half-life of the reaction, we have K is equal to 0.693 divided by T half. Now rearranging this equation, time required is 6.909 divided by K. Here T half is equal to 0.693 divided by K. Now let us take ratio of these two time, that is time required for 99.9% completion as well as for T half. That's equal to 6.909 divided by K, that's divided by 0.693 divided by K. K and K gets cancelled with one another. We have 6.909 divided by 0.693. That is 6.909 by 0.693, that's equal to 9.96, approximately equal to 10. So therefore we have T 99.9% is equal to 10 times that of T half. Question number 3.9. The rate constants of a reaction at 500 Kelvin and 700 Kelvin are 0.02 per second and 0.07 per second respectively. Calculate the values of energy of activation and Arrhenius factor E. So we need to calculate EA as well as A. So they have given us temperature T1, which is 500 Kelvin, and T2, that is 700 Kelvin. Also they have given rate constants K1 at temperature 500 Kelvin, it is 0.02 per second, K2 which is equal to 0.07 per second. So to calculate activation energy, we will make use of the formula log K2 divided by K1 is equal to EA divided by 2.303 or T2 minus T1 divided by T1 into T2. Let us substitute. Log K2 is 0.07 divided by K1 is 0.02. EA is what we have to calculate, divided by 2.303 into 8.314. T2 is 700 Kelvin minus T1 is 500 Kelvin divided by 500 into 700. Simplifying this, EA is equal to, it is log of 0.07 divided by 0.02, which is 3.5. So log of 3.5 into 2.303 into 8.314 into 500 into 700 divided by 700 minus 500. Now let us simplify this. Taking log of 3.5 using log table, then multiply 2.303 into 8.314 into 500 into 700, then divide by 700 minus 500, that's 200, and this is equal to 18,230.359. I'll write this as 36 in terms of joules per mole. Let me convert this into kilojoules. So it is 18.23 kilojoules per mole. So this is the activation energy. Now we need to calculate value of A. So we shall make use of Arrhenius equation. K is equal to A e to the power minus EA divided by RT. Making use of Arrhenius equation, let us consider temperature as 500 Kelvin. Corresponding rate constant is 0.02 per second. Activation energy we have calculated, it's 18,230.36 joules per mole. Now let us substitute into the equation, Arrhenius equation. So K is 0.02 per second. It's equal to A is what we have to calculate, e to the power minus 18,230.36 divided by R, it is 8.314 into temperature, that's 500. Now let us take natural log on both sides so as to make this simple. So ln 0.02 per second is equal to A, that's ln A minus 18,230.36 divided by 8.314 into 500. So converting this into log, I can write this as log of 0.02, which is equal to log A minus 18,230.36 divided by 2.303 into 8.314 into 500. So let us simplify this. Take log using log table. So it's log of 0.02, that's minus 1.6989, which is equal to log A minus 18,230.36 divided by 2.303, 8.314, 500. This is equal to 1.9042. So log A is equal to minus 1.6989 plus 1.9042. This is equal to 0.2053. So log A is equal to 0.2053. Take anti-log using log table. We will get the answer as 1.6044. So this is the value of A. A is 1.6044. That is the Arrhenius factor. Question number 3.10. The first order rate constant for the decomposition of ethyl iodide by the reaction, given reaction at 600 Kelvin is 1.60 into 10 to the power minus 5 per second. Its energy of activation is 209 kJ per mole. Calculate the rate constant of the reaction at 700 Kelvin. So they have given us activation energy 209 kilojoule per mole. So we'll write it in terms of joule per mole. It's 209 into 10 to the power 3 joules per mole. Also they have given rate constant at 600 Kelvin and they are asking us to calculate at 700. So T1 is 600 Kelvin and the corresponding rate constant is 1.6 into 10 to the power minus 5 per second. So temperature 2 they have given us, it is 700 Kelvin. Corresponding rate constant is what we have to determine. So we shall make use of the formula log K2 divided by K1 is equal to EA divided by 2.303 R T2 minus T1 divided by T1 into T2. So log K2 by K1 can be written as log K2 minus log K1, which is equal to EA divided by 2.303 R T2 minus T1 divided by T1 into T2. Further rearranging, I can write log K2 is equal to log K1 plus EA divided by 2.303 R T2 minus T1 divided by T1 into T2. Let us substitute all the data into the formula. Log K2 is equal to log K1 plus EA by 2.303 R T2 minus T1 by T1 into T2. So we have log K2 is equal to log 1.6 into 10 to the power minus 5 plus EA is 209,000 joule per mole divided by 2.303 into R, that's 8.314 into T1 into T2. So it's 600 Kelvin into 700 Kelvin. On the numerator we have T2 minus T1. So it's 700 Kelvin minus 600 Kelvin. Simplifying this, take log using log table, which is minus 4.796 plus second part is 209,000 into 700 minus 600 is 100 divided by 2.303, 8.314 600, 700. So we get this as 2.599, which is equal to minus 2.1970. So we get log K2 as minus 2.1970. K2 is equal to anti-log of minus 2.1970. This is equal to 6.3521 into 10 to the power minus 3, and the unit is per second. So therefore, K2 is 6.3521 into 10 to the power minus 3 per second. Thank you for watching. If you have not watched our NCERT classes, you can watch those videos by clicking on the playlist here. I'll meet you in the next video. Take care. See you. Bye-bye.